Okay, welcome to lesson 2 of unit 2 on reflections. So we've seen reflections. We talked about it a little bit in our first unit, but we're really going to make sure that point gets driven home with this lesson today. So that's the only thing we're going to be focusing on is reflections. So specifically, we're going to be talking about reflecting in the x or the y axis. Okay. And we'll talk about a different type of reflection later on in the unit, but it's going to have a different name, so we've kept it separately. So if this is my parent function, and again, defining parent function is just like the one we start with. Then if I put a negative out in front, what that does is it's a reflection in my x-axis. Now that sounds a little weird. So if we're talking about using our mapping notation, we go from xy to x and negative y. So we change the signs of all our y values. Okay. Conversely, if I am dealing with a negative inside my function, so affecting my x values, then this we would call a reflection in the y-axis. And so we start with xy, we would make that x negative. And so we're changing all of our x values. Okay, so what does that mean? In example 1, we see if y equals f of x, then y equals negative f of x is obtained by, and again, that's just what we've written up here. We change our y signs, and we change our x value signs. If we're reflecting in that. So we see this in our parent function being f of x is at -4 and +3. By taking the negative version of our parent function, we're going to change our y value. And so my coordinates then become, we're just writing this as a set, the set is one single point. My x value doesn't change because I'm not impacting x. I'm not affecting my inside of my function. I'm only affecting the outside of my function, which is my output or my y value. And so that is what becomes negative. Conversely, if we put that negative inside, then I'm only affecting the inside of the function. My outputs should match something that already exists. So when I go to write my coordinate points, I'm going to change the sign of my x value. So -4 becomes +4. My y value stays true to my original parent function. Okay. So that's how that works in a nutshell. And we can see how it reflects over the y-axis. That's why this one is called a reflection in our y-axis, because it's going over our y-axis. Whereas this one is called a reflection in x, because we're going over our x-axis. So example 2, we can also do this pictorially. So reflecting over the x-axis. So again, that means all my points above are going to go below, and all my points below are going to go above. Now, I don't expect this to be perfect because I have no specific values to plot, but I'll do my best. So I know that I should hit, well, I hit it approximately here and here. Anything that's actually on my x-axis, because it's 0, when you change the sign of 0 from positive to negative, the value actually doesn't change. So anything on your x-axis is going to be called an invariant point. Okay, and we can also call this like a critical point if that helps you think about it that way. But it's invariant because it is not changing. It is not varying. So I'm going to put those ones on here first because I know where they should be. That's too far. Here. Okay. But instead of going down and coming back up, I'm going to go up and come back down to about where my line ends, where my y-axis ends. And it looks pretty symmetrical, maybe a little bit lower. So I'm going to go up and down like that. And again, because I have no specific point values, I can't be 100% sure that I'm doing this exactly correctly. I'm just roughly estimating. Let's say that maybe this side needs to peak a little bit more over here, so I'm going to put a point there just to give myself like a target to go to. Like that. Okay. And so that's a rough sketch reflection over the x-axis, but the key thing is this invariant points are going to help you because they're on the x-axis. 0 stays 0. Example 3. So we've got slightly better values. This time we're asked to reflect again over the x-axis. So again, oops. Because we're changing our y values. So I would say if we tried to mark out these points, create some sort of scale as a reference, I would do something like that. I'm going to try and mark out where these kind of changes in my graph occur. Like that over here. Okay, again, you could totally make set a table of values and do the mapping notation and change it. That's fine with me. Whatever kind of works for you. And then again, remembering this point right here is what we're going to call an IP, an invariant point. So I'm going to put it in exactly the same spot. From there, I'm going to choose some other critical points that kind of define it. So if this was at +1 and +1, I'm going to go to +1, but my output will be -1 instead. So see how it's ending up on the other side. Same thing here, instead of +2, I'm going to be at -2 for my y value or my output. That helps me just create the general sketch of my graph, choosing those invariant points and critical points. And from there, I can fill it in. No problem. Reflecting over the y-axis. So again, that means everything on the right is going to go left, and everything on the left is going to go right. That's over the y-axis. And we see that again with that negative inside the brackets. So here, it's my y values that aren't going to move because I'm not changing the sign of my y values, or I'm changing the signs of my x values, right? Because that's what I'm doing here. So I've got one invariant point. I can mark it again in pink just to keep some consistency with the last example. Okay, again, some other critical points. Going to be these guys here. And maybe even like my max and min, just kind of as points of reference. But again, all my, if we're using mapping notation, we're going from x, y to -x, y. So anything that was negative should become positive. Like so. And anything that's positive, like these 2 points here, should become negative. So roughly here-ish. And from there, again, I'm going to try and connect my points as best that I can to make it look like the previous graph. Something along those lines. Example 5 is asking us for the same thing. So without using its words, by using this general notation, you're still reflecting over our y-axis. So again, anything on the right is going left, and anything on the left is going right. I realize I drew the arrows opposite to what I was saying. If I check for invariant points, that's always going to be my first point of reference. They're not always going to be at the origin. Okay, it just happens that our two examples here are. Okay, I'm going to choose some other critical points. I'm going to plot them. So roughly here, since I don't have any values on my graph again, maximum stays a maximum. I haven't shown anything to my y values, so that stays about there. And then horizontally, I'm going to keep it the same vertical depth, but I'm going to move it onto the left side of my y-axis. So roughly here-ish for my critical point. And again, I'm just going to connect those points. And so you can see how invariant points and critical points can be really helpful in recreating that shape, because once you've plotted specific points, we can just try and mimic how they're connected. And in this case, it's just straight lines, so that makes life pretty easy. Okay, so example 6 looks at the same idea as before. So again, take a second. What does this mean? Is this reflecting over x or over y? Is this one reflecting over x or over y? And then we're going to state the domain and range. So something that might be helpful is stating the domain and range of the original function. So I'm just going to write that up here, looking at my graph below. So my domain, again, is my x value. So I'm going from, I would assume, -3 to +5. I'm going to erase those marks. So from -3 to +5. My range is from -2, that's my lowest point, to +2. So what's nice here is that you can actually do the table of values strategy. So that's what I'm going to do, just so you can see what that looks like. If you want to give it a shot on your own, I'll just show you how I would set it up if I was personally doing this question, like I am. And then you can pause the video so that you can try it on your own. So I would set up a table where I'm doing f of x, or we're using the notation g of x. And then I would have a table for negative g of x and g of -x. So that's where I'm going to work. Next thing I'm going to do is I'm going to choose my critical points to work with. So that's anytime I'm crossing an axis is a potential invariant point. And any other time my graph really changes directions, that's another place. And any endpoints as well, maximums, minimums, that kind of idea. So moving from left to right, I've got -3 and 0. Got -1 and -2, 0 and -2, 3 and -2, and I've got 4 and 0, and 5 and +2. So once I've defined that, now I just need to remember how these different ones impact. So again, here I'm impacting the outside of my function, so that's going to be an impact on y. And because I'm impacting the inside of my function here, that's going to change and look at my x value. So if you want to pause now, take a second, give it a shot, see if you can figure out what these coordinates would be in each of these different scenarios. When I reflect over x, changing my y values, and when I reflect over y, changing my x values. Okay, so first of all, I'm just going to show you my first column. So when I'm reflecting over x, so I'm changing my y value, you'll notice that only the y values are the ones that are changing. And the impact is that my graph looks like it's flipped upside down. So I've done them all in purple so you can kind of track in between. When you're doing this on the same graph, you always want to make sure that all your different graphs are identified. So I'm going to, even though I've used a different color, I'm also going to make sure I name it. That purple is negative g of x. Okay, so again, if you want to pause and try g of negative x, you're more than welcome to do that. Okay, so looking at the blue points on our graph and the blue coordinates here, there's a couple things I want you to notice. And in general, one thing that I want you to kind of look at on your graph. So first of all, when we look at our table here, and I've completed this this third column in changing all my x values, please always be careful to be conscious of always looking back to your parent function. So I kept those y values of my coordinates from my parent function. I did not use them from this reflected over my x-axis coordinates. And that's really important because if I had done that, then I would no longer be talking about either of these equations, but I would be talking about a whole different one. I would be talking about negative g of negative x. Okay, and that's not what we're talking about right now. So always go back to that parent function in order to make an individual change. And you can make both of these at the same time. That just would have looked different than either of the ones I was asked for here. The other thing I want you to notice before we look at domain and range of each of them is that we do still have those invariant points hitting. So again, we see 100% here that, so again, we're seeing that our invariant points are showing up depending on which one we're doing. So reflecting over our x-axis, so changing our y values, has resulted in 2 invariant points. These two guys right here. Okay. Whereas reflecting over my x-axis resulted in this invariant point here. So again, we're seeing that when we're talking about invariant points, we've got them for reflecting over my y-axis, I have them showing up on my y-axis. For reflecting over my x-axis, they show up on my x-axis. So again, just kind of things to bear in mind, helpful little hints in terms of being able to be just like more proficient, more efficient when drawing these graphs. So let's look at domain and range. So again, we're looking at the purple function for this one. So my domain has stayed the same. I didn't do anything. My minimum is still existing at -3. And my positive maximum for domain is still 5. My range, because it's symmetrical here, also hasn't changed. So even though I reflected vertically, because my maximum and my minimum were kind of like opposites of each other, negative and positive 2, I don't actually see a change in that. So you might be able to predict what's going to happen with my domain and range of this function where I reflect over my y-axis though. And what we see there is that my domain has changed. I'm now at -5 as my minimum. I'm at +3. So notice that even though we were just changing the values of individual points when we were starting to graph this, the overall impact is that my domain actually is completely changed also because I was changing the signs of x and domain is looking at only x values. My range predictably should not change here, even if it wasn't symmetrical, because I wasn't changing my y values. I didn't do anything to them. So that remains the same. Now, please note one thing that I anticipate you might be questioning. You're like, oh, well, if it like flipped this, shouldn't I be writing it as 2 and -2? And the answer is absolutely not. Don't do that. We always write minimum to maximum, no matter if we've reflected in any direction. Okay, So we've got example 7 is going to be much the same. I'll let it load for a second, but feel free to pause the video at this point and give it a shot. You can use the mapping notation. You can just use your visual graphing if that's something that you're inclined to do, whichever makes the most sense for you. I'm going to skip the mapping notation for this particular time, but I will have some critical points identified. Again, pink I'm going to use for potentially invariant points, and orange I'll use for other critical points that I'm going to use. So give it a pause, give it a shot. Okay, so again, when we're looking at these graphs, just making sure that we've tried to mimic not only the points, but also the shape. So like when I was doing this, I had to redraw this purple one especially like so many times, because I'm really trying to capture that curviness, that almost like sine function, cosine function, parabola sort of esque look that's traveling through here. So you don't want to make it too sharp like a V if it's not. If it's an absolute value, you don't want to make it look like a curve. So be really conscious of shape when you're doing all these different transformations. Once we've done that, we can do our domain and range. And another thing to be conscious of is that our original function had arrows at the end, which means that our reflections should also have arrows at the end. Okay, we aren't altering our function at all. We aren't altering our domain and range in the sense that we're all of a sudden cutting it off where before it proceeded to infinity. So if you want to, it's never a bad idea to do the domain and the range of the original function. So I'm going to do that. If you want to pause the video again to try it on your own before you proceed, go right ahead. So those arrows are really important when we're doing domain and range, and that manifests actually in what we're seeing here, because there is no specified domain and range. They keep going forever in both directions, both in x and y, and vertical and horizontal distance continues. There's no non-permissible values, there's no restrictions, we don't stop abruptly anywhere. So it's kind of nice when we have these graphs because their domain and range don't actually get impacted. If we started talking about like local maxima and local minima, we do that in calculus, then we could start to get more specific, but in terms of what we're talking about here, just domain and range, then we actually don't see a change, so that's kind of nice. The last one, example 8, the graph of y equals 1 over negative 2.5x squared minus 0.5 was reflected in the x-axis and its image is shown. What is the equation of the image? Okay, so we're actually not being asked to do anything with the graph. We're strictly given the graph and the equation to help us think. So that's a really important thing to notice, is that we're not being asked for a graph. It is asking us for an equation, and specifically the one of the image. So not this function. This is not the function that is being shown. It's after it's reflected in the x-axis that the image is shown. Okay, so we're given the picture of the graph we need an equation for. So we're also told how we came about getting this graph from the original equation. So all of a sudden, we are totally able to figure this out because we know what reflected in the x-axis means. So we know in general notation, to reflect in the x-axis means to put a negative on the outside of the function. Right? Because we need to change our y values to flip vertically from top to bottom and bottom to top. So this is the original function. We need to throw a negative out in front of it to be able to say that it's being reflected. So instead of y, we can use any letter. So that's completely up to you. I'm going to use h because I don't know why. It's an upside down y. Who knows? And I'm going to put a negative out in front, and then I'm going to write the rest of my function as if it was unaltered at all. Sorry about that. So negative 2.5 x squared minus 0.5. Okay. Now, you could totally leave it like this, and that would be perfectly acceptable on the exam. If you like to kind of distribute things, make things tidy. I would have a predisposition to changing this to 2.5x squared plus 0.5, but that's just a personal thing. But this is a perfectly acceptable answer because all they've done is say to write the equation. They did not ask you to simplify it. So I'm hoping that reflecting is making more sense. We're feeling a little bit more comfortable with it than we maybe did at the end of our trig unit. I'm going to have it show up on our next assignment. I'm going to kind of lump reflecting and stretching and compressing vertically together along with the horizontal stretch and compression, just because individually it doesn't make a huge difference to what we're doing. So you're not going to see an assignment specifically for this lesson, but you're going to see an assignment when we get to like the combining functions.